the Y lab, but it's now the visual artificial intelligence lab.
Oh yeah, it's also VA. AI is anything.
I didn't realize this for a while. I was like, no, our lab name is the Y lab, so the visual AI lab. Lower by number of slides, now I just have I used to have like lots of slides. You have to go run really fast.
Oh,
but now I lowered it.
Oh,
I
okay.
made it smaller, so it's nice a little more.
I see.
More time between.
So, do you want to get started? Do you want to get started? Okay. Okay, good afternoon. So welcome to the CICS Standard Series. So today we will have Professor Klaus Mueller from Stony Brook University. So Klaus is a very well-known people in the field of visualization. So his research spanned a lot of areas, starting from late 1990 volume visualization, medical imaging, now go to also to high-performance computing, now visual analytics. Okay, so and he has taken on a lot of leadership role in the community. He was the general chair of the IEEE Visualization Conference, which including all the three branches of visualization: scientific visualization, information visualization, and visual analytics. So he's a general chair back in 2009, and he also was the chair of the IEEE Visualization and Graphic Technical Committee. So it's like technical committee for IEEE. And currently he is also the editor-in-chief of IEEE Transactional Visualization and Computer Graphics, so which is the flagship journal in our field. And I also know that Klaus also has some kind of startup company, and he last year he was inducted to the National Academy of Inventors. Okay, so and today he will be talking about high-dimensional data. And let's welcome.
Okay. Well, thanks, Charlie, for the introduction. Also, thanks for inviting me. Okay, so I just want to talk a little bit about high-dimensional data visualization, which is like the. So I don't have any deep learning. Okay, so anyone still here? So, but I did recently change the lab's name from Visual Analytics and Imaging Lab to the Visual AI lab, which is basically the same, same abbreviation, but just a different. So anyway, so just why is it now? This is okay. I don't know why this came up. So basically, I want to show you what all these things have in common, right? So we have like a spiral flow, or a MRI head, and virtual fog, nerve cell, a little slow, and MRI head. They're all spatial data, right? They're all spatial data. You can all take them and render them in 3 dimensions and understand them quickly, although, maybe you've never seen a nerve cell, but, that's what it looks like. You can color them in green or red or whatever. But, they're all of them sort of easily understood, right? Because they have a spatial, sort of a nice spatial representation that you're familiar with, like frog and the head and tomato and then spiral flow, kind of easily understood. But, so here's why is it not here? So, why is it not doing this? That's very strange. So here is some data that are also spatial, right? It's like a car, many cars. But that's only one aspect of a car. Here's another aspect, right? They're like mass per gallon, top speed, acceleration, number of cylinders, and horsepower, number of doors, and whatever. So these are really not spatial data, right? I mean, they have spatial representations, but they're not really spatial data. You can look at the sort of look at them as an attribute. Okay, so these are what's called non-spatial data. Okay. So now, how do you visualize this, right? So you can't not really make a three-dimensional representation out of it by nature, right? So you have to somehow, you know, force them into something they can look at if you want to look at it. So you can use this, you know, when you look at it like this is called a rectangular data set or data matrix, where the rows are like the typical Excel spreadsheet. You know, the rows are the data items, and the columns are the attributes that you have, or variables. You know, and then, you know, there could be anything. It could be a survey of people where the respondents are here and the answers are here, or it could be, you know, like pattern characteristics, or it could be cars, or it could be whatever it is. You know, you can always put it into something like this. And, you know, so how do you look at this, right? So you can look at the spreadsheet like this, but it's pretty hard to see any patterns there, right? So if you want to look at this, you know, data matrix, like what are my clusters and what is really going on? Are there any relationships between those different data items? Very hard to see without just look at a spreadsheet like this. So now this is basically a high-dimensional multivariate data space. Okay, so the problem is there's something called the curse of dimensionality. When n, the number of dimensions, goes to infinity, then, you know, when the side length is, there's the side length of the cube. When you look at it from a cube perspective, like each side of the cube, each axis of the cube is one attribute. So if you have n infinity number of attributes, what happens to it if the volume goes to 0? Actually, surprisingly, when the length of the side is less than 1, or it goes to 0, tends to 0 when it's less than 1, or it is 0 when the length is 1. So it basically shrinks, and the diameter goes to infinity. You know, it's very, very sparse. When you look at it this way, you can actually see that most of data are mostly here at the edges. Why is it? I have to stay here. For some reason, this doesn't work well. So not here, right? So here basically, not many of the data is actually in the core of the hypersphere. Most of it is out there. Okay, so, you know, actually it looks like this. You know, it's really a hedgehog. So there are some data points in here, some data points in here, but very few here. Okay, these are like basically data points that are somewhat dominated by some dimension and not so dominated by others. Okay, and then they end up. So what it shows you here is that it's very hard to go from one spike to another. Or what it means is it's very hard to determine because each of these spikes is equally distant from other spike. Right? So it's very hard to figure out where are my nearest neighbors. And that's actually, this is captured by this Bellman equation that says, like as dimensionality goes to larger than, let's say, already by 12, that my nearest neighbor is any point could be a nearest neighbor or my furthest neighbor. It's really unclear where it is. And that's very hard then to figure out, for neighborhood relations, to figure out similarity and to group things together. Because you know, unless they're very close together, it's very hard to figure out where are these, how things are related, sort of in terms of the similarity and so on. You know, it gets actually extremely sparse. To give you a little bit of an example of this, that you really understand this, because it's actually very daunting. Because you don't really think in high dimensions. For example, when you're doing 1D, points are very close, right? So points are just like sort of lined up. It's very simple to go from here to here to here, right? And it's you know, very simple to figure out what is close to this. In 2D, things already start to get pulled apart a little bit, right? Then you add, let's say you add a second feature or a second dimension, then things get a little sparser, okay? Then 3D, things get even sparser. Okay, so now really things are somewhat, you know, dispersed, right? Let's just think it goes to 4D, 5D, 10D, 12D, 20D, 100D, 1000D, right? So you're gonna see like how lonely the space becomes, right? It's like, you know, like outer space. You know, so it's very hard to think. There's like a data point here, so data point here, another one here. Where are the clusters, and where is the outliers? Who is my nearest neighbor? Who is not? Becomes very hard to do. Okay, and then another perspective to this is how to store this stuff and how to index it and how to find things once you want to find out where things are. Right, it gets very expensive. Let's say, you know, usually what people often want to do, and I see this often, like in papers, people propose this. when they don't really know what high-dimensional space really means, they don't have the, the required, humbleness to it. They basically say, okay, I'm going to take my space and make 16 cells, like that. So you make bins and then group them into bins. Okay, works fine in 1D. 2D, because it should be 64, there's an error there. Okay, I meant to correct this every time. So 16, and then, you got here 4,000 cells, then it's 3D. And once you have like 4D, they get 6K cells, 5D, 1 meg, 68, 16 meg, and 70, 268 mega cells, right? So it's basically impossible, even already for 7 dimensions, which is really, really, not a high dimensional at all, to decompose a volume or this hypervolume into cells, like into bins, and just store things like this way. You can sort of go, okay, here I'm going to go up here, and this is where my other guys are, right? It's very hard to do. So any of those, and this is only 16 cells along 1 dimension. You need a lot more, right, to really be accurate, right? So anyway, space and memory management is very hard to just figure this out. So you need some other representation, actually almost anything. After a while, if you go like beyond 15 dimensions or so, you just need to, do like an exhaustive search or something like this. Everything else doesn't get you anywhere. So, so this is like another thing. So, okay, exponential growth, as I said. So, so now you want to see these relationships, and oftentimes people sort of use these bivariate scatter plots, right? Because people sort of look at 2 dimensions at a time. For example, here, like here, what is this? These 2 attributes here, and you're going to see the distribution there, right? But then you get like more than, you got 2, 4, 6, 8, 10 attributes. If you want to store them in bivariate scatter plots, you basically have to make this matrix 10 by 10 matrix, right? And so to figure out how these sort of are related, how are births related to house and so on, like in a multivariate sense, you're going to be looking around a lot, right? It's just like, where is it? Like, what is the other one, right? It's very hard for you to grasp where are these multivariate relationships with these kind of plots, okay? Because, it's just unmanageable. And this is only 10 attributes, right? So if you have 20 or 100, what are you going to do, right? So it's very hard to really come up with. So what I'm saying here, what works really nice in low dimensions is very hard to generalize in high dimensions, because you're just going to be overwhelmed with the data size and the complexity of it, okay? So why are they hard to comprehend? Well, because, when you're a child, and I have a 7-year-old daughter, and I remember very closely, and you may have children too that are maybe young, very closely how she understood the world. What she would do, she would like take an object and grab it in the hand and look at it from all directions, maybe lick it and put it in her mouth, to understand what this 3-dimensional object is, right? The next time when she looked at it, she knew, okay, this is a bottle. Now I don't have to touch it anymore. Or I see another bottle and I can say, this is a bottle too. Or something that's a little smaller, bigger. All of these are bottles, right? They can start like getting sort of a map in your brain to classify the world into different object types, and then you can sort of reason with them easily, right? That's when you see something. So, it's very easy for a baby, like they learn this very fast. And now you don't think twice about when you see a bottle. Of course, it's a bottle, right? And something that looks like a bottle, you can use it as a bottle, right? So on. But when you get older, right, and you build this object permanence, basically create a mental object, a mental picture of when you see things. This is actually a very old theory. But when you are this age, you have to be a certain age to learn this object permanence. When you get older, like with 10 or 12, it's very hard for you to learn that anymore, right? So there's people that were blind for a while, and then they started seeing when they're much older. They had a hard time to make sense of the world because they never had learned what these spatial representations are. The brain sort of freezes after a while. You can't really learn more about this, right? You have to learn this from early childhood. Right? But no one told you how about high-dimensional data spaces, right? Back when you were a child. So, then that's why you don't know what it looks like, because no one ever showed you. Now it's too hard to learn it, directly, right? You need some sort of prosthesis to learn that, okay, to understand the high-dimensional data space. So, so part of my research really is to create these kind of prostheses that help you understand, navigate, and explore this high-dimensional data space. And so I'll show you a few of them. Okay, so let's go back to our high-dimensional data, which is, I like cars, okay, I confess. And so I use car as a nice example for this, because everyone understands cars, most of you, I guess. And miles per gallon here is some interesting attribute, top speed, acceleration, number of cylinders. So these are all very interesting attributes when you go car shopping that may interest you, right? That you may ask a salesperson, like, well, what's my mile per gallon, and what's my high speed, and what's my number of doors? I mean, you may be interested. And then, someone will tell you, and then you can figure out, so where are those trade-offs, right? Where are these trade-offs? So there's a nice method that is very sort of, very well known in the visualization field at least, which is called parallel coordinates. Okay, parallel coordinates essentially is a generalization of this bivariate plot that I showed you before, right? Where you have like, no longer do you have an axis here and an axis here. Now you have to take the axes and put them parallel to one another. That's why it's called parallel coordinates, right? And then you just basically take a car at a time, label the axis intersection here, mile per gallon is here, cylinders is here, horsepower is here, and just label, mark the car's value, and then connect it with this line, which is called a polyline, and then you can sort of see the signature of a car. So you can learn a little bit about this car. Okay, low horsepower seems to be like give you a little bit midpoint mile per gallon. Okay, and then here's like other things that are there. Weight, same low horsepower, high weight, could be. And then you go one car. But usually you have a lot more cars than one, right? Because you car shopping, or you have something you want to compare and learn about cars, how they look like. So you can plot all the cars. So so now this is basically general term for this, a crazy mess, right? So it's like a scientific term for that. Where you can't really see anything anymore, right? Because there's severe overplotting over these cars. And it's like they have this basically cobweb of cars. You don't even know where the individual cars are because everything's sort of disconnected. So you need some processing, okay? So you need some processing. So you can, for example, do clustering. You can say, okay, I'm going to cluster by cylinder. I'm going to take the high cylinder cars, make them red, take the green cylinder car, make the 6-cylinder cars, 4-cylinder cars. There's actually a 2-cylinder car. This is from the 1980s. I don't know what car that was. And you learn a little bit about cars now, right? You can sort of see, okay, when things have low cylinders, they tend to have good gas mileage. And they don't really have high horsepower. They seem to be low weight and so on like this, right? And then these red cars, high cylinder gas guzzlers, they don't get good gas mileage, but they have a lot of horsepower. But they're also very high, very heavy, right? So this from the 1980s, the cars from the 1980s, they were very much rawer nowadays in their sort of specifications than the cars are now, right? So really, when you have powerful cars, they tended to be much bigger and more heavy because they needed to stay on the road, right? They need weight to stay on the road, otherwise they fly off the road. So, but this is somewhat, something you could never show this to a business person, right? The business person would say, oh my God, all these lines, this is like scary, like really, really scary kind of plot, right? This is good for engineers. Engineers, okay, fine, I can live with this. But once you show this like to a business person, they'll say, I don't see anything here. So you can do something. You can compute the mean value, right? You can median or the mean value. Gives you a little bit of trend lines, some help, some crutches to understand this kind of thing. It looks a little better, but still very technical, very kind of geeky look. So here's like this other thing again. But what you can do is you can sort of create some sort of envelope around it, right? So it looks smaller. Now it looks really like Excel, right? Excel has these kind of nice sort of nice shadows a little bit on it, nice envelopes, nice pleasing color, uniform color. Now you can sort of see the population. You can see there's a lot of span width in here, in this area here. There's very low range of values in this variable here. You can sell a little bit of here, So it looks a little better. So we did some user studies and found out that people tend to like this better over this, right? So they tend to like this. So if you want to show a little bit, okay, then if you want to show a little bit of dynamics of the data set, remember there's like some areas that were less populated than others. What you can do is you can take those lines that are originally there and blur them a little bit and then mat them together, right? So now you get a little bit of this illustrative look. At the same time, you get a little bit of an idea where things are sparse and where things are heavy, okay? So it's like basically illustrative abstraction. And then when you do it for like multiple cars, multiple clusters, you can sort of create these kind of displays. And then you'll sort of quickly see there's the red cluster, the green, and the blue, and they have different kind of trends and values. and you can learn about that, right? So it's like illustrative parallel coordinates, and it seems to work out much better for like, you know, sort of a, you know, like for mainstream people than the other one. And I'll show you a little later on today. I'll show you some storytelling that you can do with this. But for now, let's go on. And so I want to show you a little bit what you really need to do with parallel coordinates. You know, you can't just show people just a static picture, you know, because, you know, this is just, you know, people want to start playing with it. It has to be interactive, okay? So here's an example for what you can bring this to life, okay? So here's like an example of this. So the way you would do it, basically, you would take down some of these ranges and isolate certain clusters and color them. And then you take down again and take down, find another range that you may want to bring down and sort of see like where there are certain clusters, behaviors in the data that are sort of, you know, coherent, and then color them individually. So you can start playing with this and generate these kind of displays where you can sort of see things now, right? And then so basically now you are in the loop, right? The data scientist can go and segment the data, whatever hypothesis they have, and play around with it very quickly, right? So interactive, fully interactive, and then save it as these kind of representations for later, and then show it to the colleagues in the presentation. So basically, interactivity is very key here, and it has to be fast, intuitive. And there's nothing more intuitive than bringing it out up and down a slider. Right? It's very simple to learn. So this is really what you need to do. But to tell you the truth, so we got really arrogant, okay, and we started like, okay, well, I think parallel coordinate, everyone will know this, right? And we used it like for a paper we wrote for a software visualization conference, where we tried to compare different, you know, what is it, different cache sizes and levels and so on for runtime or behavior of parallel programs, okay? And we showed like, you know, the trade-offs between different cache sizes, between different data, the GPU and so CPU sizes and so on, and showed each of these configurations with a parallel coordinate interface, okay? And thought, okay, here we go, you know, you can see this. Reviewers, please give us, you know, high marks for this paper, and you know, but we got like this comment here. It was very interesting. So this reviewer, this is an actual reviewer. I don't think this reviewer is here. I hope not. So, okay, multiple visualizations appear to present categorical data as line graphs, which seem a strange choice. And then went on. Figure 8, for example, that's that figure. Like, first sight appeared to be showing a change over time, but in fact, further inspection shows that the different x coordinates are almost entirely unrelated to one another, no particular order. That's shocking, right? There's such an unusual choice that I'm not sure that I'm understanding the role of the graphs correctly. So this is really a reviewer who does not know parallel coordinates, right? I mean, of course, these people exist wildly, but it's actually not intuitive. And I know I've spoken to people that deal a lot with people from the business world and from the general world, said if this time axis is not time, if this x-axis is not time, then they don't really know what it means. So it's very interesting. So, you know, so I tend to see this. Of course, the paper I don't think the paper was accepted, actually. I'm not sure anymore. So, but in any case, I take this up as a challenge, okay? This is actually an interesting challenge. So how can I make people understand parallel coordinates? Okay, what can I do without any words? Just by, you know, like some sort of illustrative technique. So, let me make the cow sound. I think I've connected the sound out. Okay, so here. Got a little bit of something for you. Okay, so how to teach mainstream users. Okay, so this is like something we did, learning visualization 1 hour. So basically, we would like, you know, whenever there's like a parallel coordinate display, we would let them see this very tiny video. It's like only like a few seconds, right? And let them understand what is a parallel coordinate display all about using a table, because everyone knows tables, like tables and bar charts And these kind of things you learn in high school, right? Everyone knows it, right? Everyone went to high school, you know, even, I think my daughter is like in elementary school, she knows what the bar graph is, right? And the table, she actually knows what tables are, right? So you learn this very early on, right? So it's basically something ingrained in you. And then you basically, we try to test this hypothesis that these things actually will work, right? That you actually can, with these kind of analogies, that you can teach mainstream users to understand what these high-dimensional data visualizations actually, you know, what they actually mean and what they can give you. Okay, so here, basically, we did this user study, and we basically would like show users a parallel coordinate display first, without any explanation, to ask them, so what do you think this is? Okay, just let them write down what they thought. So we did, I think, like 30 or 40 users. In like general, we actually went to coffee shops and like and places where you would expect like people that don't really know make visualization did this, and then we would encode their answers by the level of the understanding they would have, and then we let them play with the app and ask them again with a different example. Okay, so here's some utterings and associated with levels of understanding. So if someone said, you know, someone said that, well, this parallel coordinate display, what is it? I don't know what it is. Like this kind of thing up here looks kind of like colorful spaghetti in a grill. Obviously, this person was completely clueless, right? So it's like, and he was actually meant that, right? I don't know if it was a he or she. And then, if he or she would say, number of cylinders of the orange highlighted car is 4, 1/5 between 3 and 6, then that person would understand the representation, right? He would understand, okay, this means something in numbers, you know, below and above. So representation is understood, the visual representation is understood. Then the next thing is, you know, when he or she would be able to see like that that there are cars that are sort of clumped together. Many of them have 8 cylinders, some of them have 6 and 4. Then they would basically be able to identify groups and outliers, right? That's like a next step, right? Now they have actually reasoned with it. They actually saw there's like some clusters of things. And if they could finally understand that they could say like heavier cars have more cylinders and hence more horsepower, you know, and speed, then actually people have understood the visualization completely, right? They actually were able to derive knowledge from it, insight from it, right? That was the best they can do, right? They actually really used the visualization and learned something from them, right? So that's of course the best answer you can have, right? Answers like this. So we would like ask all these people, and they would ask them what they think and what they learn and what they see, and then transcribe group those answers into these 4 different character categories, and then mapped it. Okay. So, and we found out, you know, before and after, that really, you know, we had these kind of individuals. Almost everyone learned something. Some people learned 2 levels. Some people learned 1 level. Some people, but no one ever, you know, some people didn't learn anything because they already knew it, which is good, right? But you know, these guys already knew it. But everyone else who didn't know it yet knew more from these analogies, right? We didn't do anything else. We didn't answer any questions either, right? You just here, watch this. You know, we were actually quiet, completely silent the whole time. And also they would understand data understanding too. You know, so this was really successful. We tried a few other things, spiral graphs. We showed line graphs and wrapped them around and became like spiral graphs, which is really, spiral graphs are really good to see like periodic behavior. So we showed them that, and they would all of a sudden understand spiral graphs. We did a few more things. So this really worked out really, really well. Going from things that you know very well and find an analogy to it, and then develop from that, morph it into something you didn't know. And that was actually turned out to be a pretty good tutorial. So let's talk about, you know, so parallel coordinates, it's good, right? And we thought, you know, let's, you know, go to another domain, scatterplots, okay. So parallel coordinates have some problems, and I'll show you next, you know, what the problems are. Let's talk about another primitive, scatterplots again, okay. Here's the parallel plots. The problem is, again, when you make bivariate scatterplots, keep looking all over the place, you know, get like, you know, eye fatigue and so on, right? And so there's one way to do this. When you look a little more in statistic literature, it's called biplots. Okay, a biplot essentially is how it works is you're gonna find the 2 principal components of your data. Basically, the principal component of your data is those are the axes, 2 orthogonal axes along which the data varies the most. Okay, so this basically tells you, okay, from along here and here, the data varies the most. I'm gonna project that into that basis. Okay, so basically that's guaranteed to spread the data, the points really nicely apart, right? And oftentimes, the two major directions actually work already well. Okay, sometimes there's a third dimension that you can't show that causes the problems, right? Because now there may be variation along this axis that you can't show. They may end up in the same place, which is like ambiguous. Right now you have like 2 points that are in similar places, but they're not really the same points. Okay. So the biplot basically is this here. You have like these axes here, and these are basically the projected dimensions. Okay. Now you can also take the dimensions, the attribute vectors, and project them as well. Right. So basically, you all project everything in this PCA basis, and then you'll see certain trends here. There's a lot of points along this dimension, some points along this dimension, some of them here, right? You've got to learn something from that, right? And, so basically that's just a tutorial. But the problem with that is that, there could be like a case where this is your three-dimensional space, let's just keep it simple, and this is your two-dimensional projective three-dimensional space. And look and notice these points here and these points here, very far apart. But the problem is they will project into the same place. And this can be even worse when you're like in high dimensions, right? There's like one point, this could be like, Joe who lives in Australia, and there's like, Muhammad who lives in Pakistan, who are very different. They have like a different upbringing, different education, different income. But they all of a sudden, for some reason, because you only used height over eye color, which they happen to say the same, they all end up in the same place, right? So that can be a big problem, because now for marketing, you're going to send a mail to Joe and to Muhammad at the same time, although they're very different people, right? That they may not like your product at the same time, right? So basically you get this sort of problem with what's called projection ambiguity, because you basically projecting into two-dimensional basis, no matter if it's just two basic dimensions or two dimensions you found with the principal component analysis, no matter what it is, whenever you have more dynamics going on than two dimensions, no matter if you just rotate the space so it folds into this, you're going to have ambiguity problems, right? You're going to find out there's 2 points that are close together in that visualization that you see, but they're actually fake news, right? Completely fake news, right? But you can't blame the visualization for it, right? It doesn't tell you anything, right? Because now you see it, and then you make these conclusions, but the visualization actually lied to you, right? But not willingly, but it did. So these things work out well, if your whole dynamics of the data set really only falls in a plane, in a two-dimensional plane, but oftentimes it does not. Most of the time there is a lot more going on behind this two-dimensional plane that you don't capture anymore. Okay, so you need a visualization that can help you with that. Okay, so one thing we did was let's make this make this a little more interactive. So let people take this PCA space, the PCA space here that I show here, this biplot space that is here, and let people play with it a little more. Don't just show them one particular projection where you don't have any power to explore it, right? Let's enable people to rotate a little bit to see if things are really neighboring or things are not neighboring, and where things are with respect to one another. Okay, so we created this, what's called the Subspace Voyager. So basically, this is basically a multivariate scatterplot, just like a PCA, it's a PCA again. But first of all, we mapped, instead of mapping these, instead of drawing these ugly axes inside, which is like sort of like occluding everything else, we draw them on the periphery of this sphere. So here this is the same axis, just now when the axes are longer, they're going to get more thorough, and when the axes are shorter, they're going to get less thorough. And then map the points into it, just like a PCA display. But we'll basically let people explore that. So now you can basically explore it. So now you can basically go and rotate this three-dimensional subspace. This is a generalized three-dimensional subspace. You can rotate it around, and now you can sort of see how this green cluster really corresponds to the blue cluster and so on, right? You can really learn that now, right, from this interacting. Of course, you may now say that, I don't want to do this rotating all the time. It's so painful, I'm getting like fatigue in my mouse button, right? And of course, you can have an interactive view optimizer, right? You can run an algorithm. We use a particle swarm algorithm that will optimize the display, will rotate it perfectly so things are perfectly spaced apart. You can do this you can do this just in the three-dimensional subspace that's captured in this PCA, which is captured in this ball, or you can optimize it over the entire space and find the perfect ball that represents the certain, good sort of decomposition of your clusters. Right? All you have to do is really optimize for decomposition. You need a nice little loss function that tells you, okay, green, blue, and so they're nicely separated, and then you just optimize for this, okay, and then you can create this sort of displays. This is much better. This isn't just a mouse click optimized, right? You can also do mouse click, give me the best 3D subspace. And then what you can do is you can say, well, oftentimes when you rotate this ball a little bit, you think, if I could just go escape this three-dimensional subspace that I have now and could go in another one that's a little next to it, I could separate these clusters even better. But you can't do it because you're always stuck in this space 3D, in the space of these three PCA vectors. But but we have actually provided this functionality where you can go and take the mouse and just move the mouse button click, move the mouse into a certain direction of an attribute, and then it will basically start emphasizing it more. So I'll show you this again. Right? So you can start like really just pipeline revenue. This is like an attribute. You just move your mouse, and what it will do, it will make the 3D subspace that is captured in this ball, will emphasize it more in terms of pipeline revenue. So this has a greater weight. So basically, you're moving from one subspace to another one that's sort of slightly in a different orientation. Okay, but the user will never know anything about subspaces because it's all implicit, right? All you really do is navigate with a mouse, right? And try to figure out. You have a goal and you can fulfill it by doing this kind of thing, right? So you can basically prove a hypothesis by simple mouse interactions without knowing there's anything about high dimensional space. The user doesn't have to know that. It's just a matter of like emphasizing things and then by magic see it, right? So that's basically a very nice property of this. And you can also edit and annotate the clusters, of course. And what we also provide, you can save them, you can put them in the trail map. So whenever you like one of those visualizations, you can put them on the right-hand side, you can put them in the trail map, and then you can go and explore that trail map, animate between that. So you can put it there, right? And then you can go from one to another, I think. Maybe not. You can travel from one to another. I don't know if I've ever visualized. Okay, I think I have this here. So you can basically create a path. You can create a path and then you can start moving from the path. And now you can basically create a sort of trail. You can sort of create this voyage across the high-dimensional space that connects these different subspaces that you liked, and you can sort of see where they came from. It's like an interpolation between. And then you can sort of learn about this space nicely. So you can sort of quickly, you can do it faster too. Right, so here you can basically go quickly along this prescribed path. Right? So you see the yellow thing goes back. So this is a nice way of sort of, like once you have saved all these, to quickly sort of go through what you've learned and sort of see where things are coming from. If there's anything interesting between, you can learn that from this sort of walk across the high-dimensional space. So then another thing that often people find, I told you before, right, is even these point plots, they're somewhat, scary to look at, and oftentimes they're a little bit overplotted, right? There's like oftentimes, even though you optimize the view, still you can't really separate because it's still a two-dimensional projection of points. So you want to be a little more clear how are these clusters related? You can move them around, but it's sort of tiresome to always move the mouse. So wouldn't it be nicer if you could sort of find something that way you don't have to constantly rotate and look around? Because when you rotate and look around, this is called motion parallax, right? By motion parallax, you can quickly sort of discern three-dimensional relationships. That's what happens all the time. When you move back and forth, I can quickly see that you sit in front of him. Right? I couldn't maybe not see this if I looked straight on, but if I do my motion parallax, I can quickly tear apart these three-dimensional relationships very easily. Right? So without VR helmet, right? I just do it by motion. And this is exactly what this trackball does. It does the motion parallax. But it's kind of tiresome. What you can do is, we can say, okay, I'm going to render those points further back, a little less transparent. I put basically, put some fog into the scene, so things are further back, a little less seen. So it gets a little better, okay. Or I can do three-dimensional rendering. So this is like from here, put a little fog in the scene, or actually create three-dimensional shapes that encapsulate the point cloud, right? So this is now here, right? So it's basically the same point cloud, now just with a three-dimensional shape fitted onto that, okay? So the way you do this, you take the three-dimensional point cloud, you do a little bit of blurring, then you run an algorithm called marching cubes, and you shade it with ambient shading, so there's no, enormous is hard to find, so you do like ambient shading, so you get a little bit of a depth relationship, a little bit of occlusion, depth cues and so on. So this looks very good, right? So, and it really shows you quickly that these clusters are sort of interrelated. What is the back, what is the front, what's bigger, where are the outliers? All of this is very nicely shown. And we've ran this, we did user studies on this, and people learn more from this, right? They could answer questions about relationships of different clusters much easier by looking at this than by this, right? And it's the same thing. It's just basically now rendered in 3D. And since humans are very familiar with three-dimensional shapes, this is a good display to use, right? Because the three-dimensional world is usually like this, right? There's like solids in space, right? The three-dimensional world rarely looks like this, right? Okay, so rarely looks like this. Three-dimensional world more looks like this, right? So this is basically, so humans are already by nature attuned to see this kind of stuff very easily. So then of course you can also navigate it. You can put it in a trackball, look at it from different directions. Okay, so this basically 3D, subspace, and then, okay, I think you saw that already. So next thing I want to talk about, okay, now we looked at this, we had looked at this point cloud in a trackball, we looked at it, we saw parallel coordinates, and all of these things, they're sort of all like high-dimensional data, like in the raw nature. Like parallel coordinates was like the raw data displayed in this axis system. The scatterplots was also raw data displayed in this coordinate system. So now is there like a way we can sort of abstract it more and see the data in more like in another way, in more like a geographical kind of way, right? Where you can sort of see these similarity relationships, not in terms of the points as they are close to one another, but more like in a layout kind of way. Okay, so this like visualization by maps is basically the way to go, right? And visual maps are very, very common. I'm trying to make visualizations that are understood by most people, right? And maps is something you see all the time. And these colored maps you see all the time too, right? For example, this is here, how people call soft drinks. Okay, so you guys are here, right? So you call it pop, right? Is that true? Aren't you here somewhere? Where? Oh, are you here? Where's Indiana? Is this Indiana? Ah.
This is Indiana.
This
is Illinois.
Right?
Oh, this is Illinois. I'm sorry. This is Indiana. Okay. Okay. You guys call it still okay. You call it soft drink. You're like bluish.
Yeah,
pop. Okay. It's a little bit in the middle. You like caught between. So okay. So New Yorkers all call it soda. Okay. So I'm from New York. So we stuff in soda. Here, of course, they call it Coke because it's close to Atlanta. Right, so which is interesting. Super Bowl actually has Pepsi commercials, which I still don't understand. But anyway, and here they call it soda on the West Coast. Here's also this sort of, I don't know why the soda is here so prevalent. Anyway, it's a nice map. You can look at it, and we have got discussions about it, right, as we just had. So it's a nice communications piece, right? You can sort of look at it, study it for a while and then make your conclusions, and it's kind of interesting to look at, and it keeps you busy for a while, and you sort of get a little bit of something out of that, right? So can we not use also maps to visualize high-dimensional data? Okay, so that's the question, right? So of course you can, and I'll show you how. So this is not, maybe for many of you is not new, but I'll give you a little bit of a nuance to this. So basically what you want to do is you want to basically create a map where the distance that the 2 points have in high-dimensional space is the same, reproduced in the two-dimensional map. So you want all the points, pairs, every point pair that you measure should have the same distance also in the two-dimensional layout. Okay, that's what you want. Then it's a good map, right? Then it's sort of a good representation what you have. So it's not like these linear projections that I showed you before, right? They were all linear projections. They basically take the points, project them into a basis. But this is not going to enforce that neighborhood, right? This optimization, map construction will enforce it, right? And I said it, you have to actually minimize something here, which is called stress, or you can also call it loss function, whatever it is, right? So basically here you try to minimize the distance something had, 2 points have in n dimensions, minus the distance those 2 points had in 2 dimensions, do this for all the points, and normalize. And then basically you want this, ideally you have this 0, right? Ideally every point pair has the same distance in 2 dimensions than it had in n dimensions. And of course, only in the most trivial cases you can actually succeed in doing this. Most of the time you can't. And when things are interesting, you have to somehow find a minimum. So there have to be run an optimization algorithm for this. So, so you can use, there's any types of algorithm, like iterative procedures that run over thousands of iterations, move things around as small increments until it looks okay, right? Until the stress function is minimized. So this is well understood. So one of these algorithms is multidimensional scaling, another one is TSNE. So they all do this, right? They all will create sort of a map. So here's like a, here's kind of a map like this. So these are the cars from the 1980s again. Told you I like cars. So, here's like the cars from the 1980s, and when you map them like this, you find out European cars are here, and here the yellow cars are the Japanese cars, and here the US cars. Okay, you find out from this map, you learn a few things, just like before, right? You learn this is the type of car, European, Japanese, and US car, and I also learn who is sort of close by spatially and who is far away, right? And then I learn that basically, Japanese cars are between the US cars and the European cars, a little closer to the European cars in the 1980s. Okay, and then, but they try to be also US cars a little bit because they want to sell some cars in the US too, but they tend to market them. But unfortunately, because the Japanese have a similar, infrastructure than Germany or Europe, small, like, short roads with like clustered sort of cities around like small countries, they tend to build these sort of smaller cars that are not meant to be driven very long, right? And so on, right? And don't haul a lot of stuff around like trucks. So, and they don't tend that, So basically, that's why they're a little close to European cars, but they really try to sell stuff in the US. So they try to be a little more like the US, but they just couldn't for some reason. But you don't know what it is, like what makes this car different, because you really want to know why are these Japanese cars a little different in the US than a German car or the European cars? What feature is actually different from this? You can't get it from that at all, right? You don't have any way to figure out like why is it like that? You say that it is like this, but you don't know why. So but you really want to know why, right? So this guy also wants to know why why I married my mother. So are these clusters so different? Why? Why is it? So they want to ask this guy here. And so what you need to do is we need to map the attributes to somehow we gotta bring in the attributes into the game, right? So to see like the relation of these data points with the attributes and see where they excel and where they fall apart, right? So, so how can you do this? So I show you like a little example using an example with college data, okay? So ideally, let's you go to college, you guys, probably all have to make the decision at one point where to go, what college to go to, right? And there were like, things you have to consider. Okay, I'm picking 3 of these. Like tuition was probably something, unless you're filthy rich, you didn't have to, but tuition may be something, probably most your parents are probably more concerned about tuition than you. You probably were more about athletic school. I want to go to a school with good athletics. Like Notre Dame is like such a school, right? Has a good athletics, right? It's like an amazing football team. Academic score, of course, but your parents are probably more interested to get good academic score. Maybe you are too. But anyway, there's like 3 already goals. There could also be other goals like nightlife and weather, and there's a lot of these kind of attributes that you may be interested in. Let's pick 3. So, if let's very simplistically shown, you say, okay, so here's like, you draw this Venn diagram kind of algorithm around, Venn diagram representation around it. And you say, okay, I want to definitely be outside this tuition circle because I want to pay a lot of tuition, because I want to be out here. I want to be inside athletics. I want to be inside academic school. This seems to be pretty good, right? This is like inside good athletics, inside good academics, outside this evil high tuition area, right? So this is perfect. But then you learn, when you plot your colors into this space, you learn that, unfortunately, no college of that kind, right? There's just no good college that has all of these. So now I have to choose, make trade-offs, make decisions in the presence of trade-offs, right? I have to like say, okay, well, I'm going to pick athletics. I'm going to pick school number 1 because I really, really want this football. I want basketball. And then I'll just go to, I go to like I go to like, these online courses and learn about academics. Okay, I can do this. Or I can go to school too. I have good classes. I learn a lot. Make my way into the world. But then I watch the schools I watch the athletics on ESPN. Or I go to school 3. I go like kiss up to grandma. Maybe she gives me some money. Or I take up a bigger loan. Whatever it is, right? I go to that. But these are decision processes now. And you can sort of look at this and just think about, okay, just think about this is the world, the way it looks like, and then, what I'm gonna pick, okay? So basically you wanna how you construct such a map, which is called the data context map, okay? How do you construct that map for high dimensional data? This is just 3D, but let's say you have 10, right? And you have lots of points. So how do you construct such a map? So the way you do this is basically you'll make a layout that is dedicated to the data, like you do an MDS layout that just represents the data, like the collages for this in this case. These are a bunch of Gaussians. They're sort of laid out with a multidimensional scaling, so you can clearly see the different clusters. And you can do the same thing with the attributes. You can also measure the similarity of attributes. Remember that's the similarity in the data matrix. That's the similarity along the data items, and here is the similarity along the attributes or between the attributes. But if these vectors are very similar, then they're very similar in terms of like things like, for example, tuition. We're going to later on like academic score and tuition tends to be very similar, right? The high in terms of like measured over all the schools. So then you have to somehow bring them together in some ways, okay? And there is like, create a sort of layout where both of them are at the same time. So the way you do this, essentially, you have to figure out, merge these two data spaces. This is the data space that is brought up by the variables, which are the attributes, and these are the schools in it. And these are the data points, and these are the attributes of it, right? It's just basically take the data matrix and transpose it over, right? The data matrix like this becomes this, and if you transpose it, now the attributes play the role of data, and the data play the role of the attributes, you're going to get this. And then you just have to basically bring them together like this, and eventually what you end up doing is you compute the similarity matrix over the data points, like in this case university, like which university, so here could be university 1 and university 4, and this point here tells you how similar university 1 and university 4 are in terms of the attributes it has. Okay, this is basically this n by m, where m is the number of universities, the similarity matrix. And here, this is the similarity matrix of the variables that tells you like how, over the data I measured, how related is tuition with the academic score, how related is tuition with the nightlife, or how related is athletics with nightlife, So basically, this could be nightlife, and this could be tuition, and here tells you how related tuition and nightlife is. This is the similarity. And then here, this is just the values it has, right? This is basically the school, and here are the different values, and here are the values of different schools. So this basically you need to bring all these together and then put them together in a single matrix. And once you have the single matrix, you got a bunch of values, then there were similarity relationships, and then bang, you can just use MDS and lay it out, right? And then you create something like this. So here's like basically my space that shows you the attributes and the collages in one space, and the 3 things are enforced here. First, because of similarity relationships that are enforced with the matrices, right? So I can see attributes that are close together are actually behaving very similarly in terms of the data. Okay, so basically academic and PhD per faculty, the higher the better the school, the more students the professor tends to have. Okay, the more PhD students the professor tends to have. You also learned that score is related to tuition, right? So the higher priced schools tend to have a higher academic score, right? And then nightlife is here. Nightlife is very heavily dependent on athletic. So you guys are all party animals apparently because they have such a good athletic score, right? So still Notre Dame is not here, no. But so here you see the Ivy League schools that are all focused around here, obviously, right? Because and they're also close together, like UCMU and Harvard and Yale. They're all sort of similar. And then down here are like the party schools, the college schools, and then and so on, right? So basically, this is a display that has all of this. But the one problem with that is it's still how do we really navigate it? So what you can do now is you can say, okay, I'm going to create I'm going to start setting these schools that I like. I'm going to select them like a Venn diagram kind of way, right? So I'm going to say, Okay, why is it doing this? Okay, so I'm going to take the tuition slider, for example, and I'm going to put them into an area where I'm comfortable in, right? So I can't really pay those high-priced tuitions. I'm going to lower that tuition slider down a little bit to like $20,000. And then you can see, wow, you know what? I cannot afford Yale, Harvard, Princeton, any of those. I can't go anymore unless I get a scholarship, right? And but I can still afford these ones, Virginia and you know, what is it, San Diego, and I can go to those still. Fine, you know, that's great. So now let's see, you know, this is fine, you know, here are the affordable schools, but, and also what I want to say is, see how these you can faintly see, the projector's not that great, but you can see the green areas. It's hard to see, right? I don't know if I should, it's kind of the light. Oh, you can see, slightly, right? So there's some green. Huh? Oh, this one's better, okay. There's like some green areas, so it goes like this here, green area here, green area here. Right? So these are basically the regions where I can afford. These are the schools that fall in this region I can afford. And then see that these areas are very sort of odd-shaped. They must be odd-shaped, not just like round like the Venn diagram before. They're odd-shaped. Wow, almost over. So that you know, they're odd-shaped because it's a projection of a high-dimensional space, a warp of the high-dimensional space into a 2D space. So that's why it's warped. Okay. So you can also do a path across. Right? You can. Oh, I didn't say this. So here, okay, you can go here, and here you can basically create a display where now you have academic and tuition in the same space. Right now you can see these overlap zones. Right? You can sort of see these are like sort of schools that have low tuition at the same time have good academic score, and then you can bring in academics, which is athletics, sorry, and then you learn that there really is only one school. There actually is a dream school. There's only one school that fulfills all three criteria that I have set. They fulfill, and this is University of Virginia. Okay, that is actually the one that has low tuition, good academics, and also good athletic program. You can learn this by this, right? So you just explore the space. You can take other variables and limit them and play around. You know, in a single picture, you know, all you know, completely uninhibited, right? There's no, you don't have to go anything, project things and find things. It's just simply seen by a simple map, right? You can also go between two extremes. For example, you can say college 1 and college 2. You know, these are extreme colleges. One of them has a really good academic score, and one of them has a high population in the school, in the you know, city. Then let's pick those two extreme schools and say, okay, I'm going to go along this path. I'm going to sample all the schools that are sort of good trade-offs between the two, right? So here, there's like this. This is a good academic one. This has good population. All of these along this line are sort of trade-offs, okay? And I can create this landscape from this, right? So essentially what this is, MIT versus Stony Brook. So MIT has a good academic score, and Stony Brook has the best cost given the academics. So what this really is, it's like a Pareto path, right? It's a Pareto path. The Pareto path is the path where, given mile per gallon, for example, you can't get, you know, anything on this Pareto path is basically a point where you can't get any better. You know, when you here optimized here, then any other choice would lower the, you know, this one has good mile per gallon and has the best horsepower you can get. This car here has lower horsepower to say mile per gallon. So this is the best school given a certain attribute. And you can extend it to high dimensional space, and then you can create these sort of paths. These are the worst cars, but you can't get any worse than that. And this is the yellow path, right? So you can basically see which are the different, you know, alternatives that I have to go from one extreme to another. And I can sort of look at this like this. So you can sort of see that Stony Brook provides the best bang for the buck. It's the least expensive school where the academics is the best. And you can see this, read this in many reports, right? It actually does really give you the best academic score. If you don't want to pay a lot, the best price, there's no school that gives you a better price and then has the same academic value. Stony Brook is the best, right? And you know, sort of, it's like a nice sort of way you can see about this, right? So I want to show you like some of work here. You know, let's get it to the end, right? When did I start? I started 4. Did I start at 4? Yes. Okay, let me show you, let me go to the end and bridge over these things and show you some other stuff that I really like to show you. So yeah, I was thinking. Okay, so let's go here. Okay, so you know, spurious correlations. Okay, spurious correlations. You also always have like probably learned about correlations. You know, and many of them are spurious, right? For example, here the divorce rate in Maine per capita consumption of margarine, right? They seem to be perfectly correlated. And then you really basically, you could say like, you know, like whenever you eat more margarine, then you know, the less margarine you consume here, right, the less divorce rate you have in Maine, right? So basically you could say like, eat less margarine, save your marriage. Okay, that could be one slogan that the marketing campaign would show, right? Or here, you know, save your marriage, eat more butter. Right? This could be like this could be like an advertisement that is shown somewhere, right? Scientific studies have shown that if you eat more butter, that it's good for your marriage. Have you not read these things? All the time you read them, right? That's like a typical, but it's all founded in spurious correlations. You know, this is like a very dangerous thing. Nowadays with fake news, and I really point this out, right? This fake news nowadays, a lot of this is based on these kind of idiotic things. A lot of these are based on these kind of stupid studies that someone did, right? And I want to like, you know, do something about this. And what you really need to do is you need to derive a causal model. Okay, you need to derive a causal model, which is a controversial topic because oftentimes people say causal correlation is not the same. And actually, you do need better algorithm to find causal relations. So instead, here you have the correlations of a car. Cylinders correlated with weight, and horsepower, and mile per gallon is correlated with the weight, negatively correlated. So these are like correlation. And then you put here the causal links to actually see cylinders cause weight, and weight inversely causes mile per gallon, and so on. These are the causal relations. And you can learn that from data, right? You can basically, you cannot just compute correlations and plot it. You actually have to do causal inferencing on your data set. So I'm not going to go into it how it works, but I'll show you, or rather show how we implemented it. Okay, so basically you can see this here. You start out with the data set, and
to demonstrate, we use the auto-MPG data set. After setting up, a causality model is generated and visualized. We see here each edge is accompanied with a green plug.
So here you basically see this causal model of a car. You'll see, okay, it's hard for me to read it. You'll see that horsepower causally is related to what is it? No, what is it? Oh, I can't read it. What is this? Displacement. Displacement causes horsepower, right? So the bigger you make the engine, the more horsepower you get. Okay, displacement is the amount of piston range, right? And then horsepower causes time it takes to go to 60 miles an hour, right? So the more horsepower you have, the smaller gets the time, right? And also horsepower causes the weight to go up, because the more horsepower you have, the heavier the car needs to get to sort of stay on the road. And then weight inversely causes the mile per gallon, right? So the more weight you have, the less mile per gallon you will have, right? So the basically more efficient the car gets. So this is basically, learn this from a causal model. Okay, this when you derive this causal model, inferencing, which we have done, you can get this kind of thing. But what's really exciting about this is that it can really give you some really good hints on car design. And this is really what causal models are really good for, decision support. How are things related, and how can it drive my certain design decisions? For example, if you look at like this here, right? So you may ask, is there a causal relationship between displacement and time it takes to 60 mile per hour? Okay, because it's not fully expressed here, right? Before it wasn't in there, but now I'm actually trying to find out. And what I'm going to do is I'm going to add this edge. The user goes into the network that is initially computed and adds this edge and asks, is this edge, addition of this edge, adding this edge, does it make the model complicated, complex? Because adding edges make the model more complex. But is it going to give me more expressiveness out of it? Does it give me more regression sum out of it, right? And if indeed this is true, if it adds more power in the regression, then that it adds in the complexity, which is measured by something called the Bayesian Information Criterion, or BIC, then this is a good one, right? So this is basically a positive effect, right? So basically I learned from this, displacement indeed, decreases the time it takes, like from the data that I have, right? There's actually a causal relationship there, not just a correlation, causal relationship. So now I can go and say, okay, That's great. But then you can say, oh, good, I make like a bigger car. You know, I make my engine bigger, and then I can say, well, it's great. You know, then I'll make a car that is more faster and that gets me, you know, that has better acceleration. That's perfect. But then you may think, oh, but you know, I learned here displacement, I make it bigger, it increases my weight, and then, you know, makes my mile per gallon small, right? And then basically I make an inefficient car. So maybe it's not easy to market such a car if it takes more gas. So I can test that now. I can say, is there indeed a causal relationship between displacement and the mile per gallon? And turns out if you do this, it's not, right? There's no causal edge here. Actually not, because the model is less powerful than before, right? So now I actually learn that there isn't really a causal edge here. So what this means for design of a car, I can now inform my engineers. I can say, okay, guys, I know for sure displacement, given the data I have gathered, you know, that I have already available to me, given the data is enough proof that displacement really does decrease the time it takes to go to 60 miles an hour. But I have also shown that displacement does not directly decrease the time, the mile per gallon, right? So basically it goes through the weight. So all I really ask you for, make a car that is less, that keeps the weight steady. Right? I make the engine bigger, but make the weight smaller, so I can actually gain something. So basically now you can tell the engineers will think about this and say, okay, I'm going to maybe use aluminum, or use a better efficient frame, or other material that is lighter, and support this sort of, make up for this increase in displacement that usually would imply more weight, right? So basically this is a nice engineering consult, right, I can get from this causal graph, because now I basically understand the concept of car, and I can design the car correctly to meet my specifications. And I can also draw it like a path diagram to make it a little easier to read. So that basically, I had a few more things, so I don't know if you want to see that. But I think we should close now, right? Because we have to do a question and answer. So basically, one thing I want to say about the final thoughts that I often get before you ask the question. So if the data is too big, what you can do is data clustering. You can just cluster data and do stratified sampling to remove some of the data, but use stratified sampling. Basically, cluster first and remove a certain percentage of my clusters and keep the outliers. Then you basically have the same data than before, just less heavy. Okay, that's number one. And then secondly, if your data are not numerical, like images, video, and text and so on, right? You can also use these techniques. All you really have to find is like features in the images, features in the data, features in the text that can sort of represent what you have. Like you can count the number of edges, or histogram, something like this to get this out, and then and then so on. So this is my group from 2016. I have a new group, or some of them are still here. Most of them not here anymore. Well, some of them are here. So so basically I have a very active research group, usually 8 to 10 PhD students, and funding from NSF and so on. So so work a lot on interesting stuff. If you want to see more, you can always go to my webpage and read some more papers. And almost all the papers have a little bit of video with it. You can learn about that abstract and so on. So if you have any questions, please let me know. Then I can answer them.
So maybe we have time for a few questions.
I come from the engineering field, and I was curious with the 3D visualizations of clustering and basically visually picking apart groups. It's great when it's interactive, but when I need to put that into a journal paper that then needs to get submitted, you mentioned some optimal, basically finding the optimal kind of view for these clusters to distinguish them most. Can you elaborate a little bit more on that?
How I find the optimal? That distinguish them both?
Yeah, it's like a 2D representation.
Oh yeah, so that basically there is criteria that can tell you like that what constitutes a good cluster and what not. Like for example, there's something called DISC that tells you like that shows that plots that looks at a certain clustering, okay, a certain projection, and figures out, let's say they're classified. Of course, they have to be classified first, like there's a green and a red and a blue glass, for example. Figure out if a point look at every point, for example, and see if it's closer to the center of its own class than to another center, to another class's center. And like if things are very nicely sort of spread apart, then every point will have that, will fulfill that, right? Every point will be closer to its own center than to another cluster's center.